Anyone have, I mean, I know at least one person had trouble finding them. Anyone else have trouble locating what I was talking about? Yeah, okay, so go to, so to find the problems, go to D2L, and I think it's materials content. I'll materials content, and then it's one of the categories in there. Let me, did I what? No, I didn't. Okay, so D2L. Yeah, we're going to skip that calculus set. Okay, so materials, content, and course information has the syllabus and stuff. Current lecture notes are the PDFs of the lectures. Homework problems. These are all the different categories. Calculus is the first one. We're skipping that. Feel free to, try to do those problems if you're curious, but I think you're doing enough calculus without me. So go to position versus time. And then the first two questions are sort of unit conversion type questions. Okay. And corresponding to the homework problems, homework solutions, they're not solutions for everything, but if you go to the solutions for position versus time, let's see, there is one for 1 and 2, and then it skips a few, but just solutions have like solutions to selected problems. Anyone else have any other questions about it? Yes. Yeah, like significant figures sort of related. I really don't care at all. You can round as much as makes sense to you. Yes. I just want to see you do it the right way. And then when you get to chemistry, they're going to just attack you constantly for your mistakes, small mistakes and significant figures. And so I don't feel like I have to worry about that at all. Okay. Um, Any other questions about D2L or anything that's been confusing so far? Anybody looked for the videos on YouTube and had trouble or anything like that? Okay. I did put, excuse me, I did put this link to the playlist for the lecture videos, so that should take you right to the list of all the videos, and then you can choose what days you want to watch. So last time we just started talking about, so our first physics topic was kinematics of particles along a line. And I said that those are going to deal with position, and there's a related quantity called displacement that I'll bring up, but that won't take long. Time, velocity, and acceleration. And we just got into defining position. And so I'll go back to that. So we're talking about this. And the SI units are meters. The units always have to be units of length. And we talked about the two things that have to be defined before you can come up with a numerical value for position. Anyone remember what those are? That's right. So before, that's right. So you have to, so along a line, there are two directions at any point, and you have to choose which one of those in your analysis is going to be your positive and which one's going to be your negative. So those are the two things you have to choose. You can choose a zero position. That's like a reference location. And which direction is going to be positive. Now, a lot of times we don't want to just, like in this class, I mean, maybe every time, for us, we don't just want isolated values for position. We want relationships between position and time. And so we usually want to know how the position varies over time. In other words, what we want is position as a function of time. So we're looking for position as a function of time. And in order to get that, we need to choose a third thing. So we need to choose, there needs to be a third thing that's chosen. And that is an instant corresponding to zero time. Essentially what we're doing there is we're turning on a stopwatch. Okay, our zero time is when you click on the stopwatch. And then everything that happens after that is measured in relation to that zero time. And one thing to notice, there's no mathematical reason that this has to be true. Obviously, we deal with functions of negative numbers all the time mathematically. But in physics, we don't tend to deal with negative numbers. So notice we won't ever use negative times. That's really more just a convention than anything else. So your zero time has to be before any of the stuff you're trying to measure. No. Okay, so what happens if you choose these three things? So let me do an example. And what I want to show in this example is that all of the answers that we're going to get, all the physics, I mean, through the whole semester, depend on these three choices. They're not like what's the function of this thing as it moves around? What's the position as a function of time? Well, your answers depend on these three choices. They'll change if you choose these three things. Okay, and that's just how it is. So someone else might get different values. There are certain things that'll be the same, but our answers depend on these three things. So let's say that there's, okay, so this is the shore of like a lake. And somewhere out here in the lake is a raft. And a little further out is a buoy. And there's a swimmer standing here on the shore. And let's say that this distance is 50 meters. So based on that, you can tell that this guy is about like maybe 20 meters tall. Okay, so 50 meters. And let's say this is another 25 meters. And we want to plot a position versus time graph. And we want to do it in, uh, so here's what the motion is. So the swimmer starts on the shore. Um, Swims to the buoy, swims to the raft in 2 minutes. Swims to the buoy in 1 minute after that, and then swims back to the raft in 2 more minutes. So he's getting a little tired. And we want to plot the position versus time graph. Well, to plot a graph of position versus time, position is going to be a function of time. So we know we need to make these three choices. We need to choose where our zero is, what our positive direction is, and what our zero time is going to be. Okay, so let's do it two different ways. So first, we'll choose the zero at the shore, zero position at the shore. We'll choose the positive direction to the right. And we'll choose the zero time when the swimmer leaves the shore. And then second, we'll choose the zero position at raft, the positive direction to the left, and the zero time. Well, we know we can't analyze anything that happens before zero time because we're only using positive times. So this time, let's choose zero time 1 minute before the swimmer starts swimming. Okay. 1 minute before the swimmer leaves the shore. And let's just look at similarities and differences between these graphs. Anybody have any questions about what we're doing? Okay, so yeah, what does it mean? So that's just saying, so think of zero time as when you click on the stopwatch. Okay, and that's just saying that instead of clicking the stopwatch right as he leaves, the person clicked on the stopwatch, happens to be a minute before he leaves. Okay. Um, okay, so I'm going to, before I go into the specific cases, I'm going to um, just a simple representation of what's going on. And this will be useful in both of these two parts. So I'll draw it sort of like a, so here's the, um, here's the whole like domain of this swimmer's motion. And here's the shore. Here's the raft. Here's the buoy. So these two, the distance between these two is 50 meters. This distance is 25 meters. And the motion, and this has nothing to do with choices of zeros or directions or anything like that. The motion starts here, goes to the raft, to the buoy, and back to the raft. Okay, that's what the swimmer does, whether a physicist is watching or not. You know what I mean? But the position and time labels are going to change based on the choices we made. So for part A, so for part A, we said that zero position is going to be at the shore. Okay, so this is our zero position. Whenever the swimmer is at the shore, the label of that position is 0. And the positive direction is to the right. Okay, so if you start at 0 and go 50 meters in the positive direction, what's the position? Yep, plus 50. And then if you go another 25 meters in the positive direction, what's the label? That's right, positive 75. And for time labels, let's say, well, we know that time equals 0 is when he's at the shore, so that's 0 time. 2 minutes later, so if you start at 0 time and add 2 minutes, you have 2 minutes when he's at the raft. Another minute makes this 3 minutes, and another 2 minutes makes this 5 minutes. Okay. And so now we can just start plotting these points out on the graph. The positions that matter are 50 meters. This is position on the vertical, time on the horizontal. We're always going to put time on the horizontal and position on the vertical because position is always a function of time. You can't be in two places at once. Okay. And so since in math you've never drawn a function of, well, never say never, but I'm guessing, let's say almost never, drawn a function on drawn the function value on the x-axis and the independent variable on the y-axis. So that's what we're going to do here. Position is always going to be vertical. Time is always going to be horizontal. And then the other point that matters is 75 meters. And the times that we care about are the ones that are labeled here. So 0, and then 2, and then 3, and then 5. And now we're just plotting points. That first, this first instant on the graph, or on this sort of whatever that thing is 0 time, 0 position. So that's represented here. Next is 2 minutes, 50 meters. So that's here. Next is 3 minutes, 75 meters. So there. And next is 5 minutes, 50 meters. So there. And everything we'll deal with in this class is going to be a smooth differentiable function. So I just put little curves on it, you know, but all we know really are the points from what's said. Yes?
So you don't add it wouldn't be 5 minutes, 100, since you already traveled.
That's right, you don't. That would be if we were tracking like distance traveled over time. But for position, we just want to know when, like think of every spot as having a position label, and that's what we're looking at. And that means that if after he got back to the shore, he ran back to the fish house, that would be moving in a negative, you'd have negative positions because that's going from 0 in the negative direction. Yes? Yeah, so what we're given is that it takes 2 minutes to get to here, and then another minute to get to here. So those times are just adding on. Yeah, and so it's 2 more minutes to get from here to here, and so 3 minutes plus 2 is 5. So the times just keep adding up. Even if the positions are going negative, times never go negative. Any other questions about that one? Okay, so now we're going on to part B, and I'm going to use that same representation I used here. Now all these labels are going to change. Okay, so I'm going to erase the purple and the red stuff, and we'll rewrite those. Whoops. Yep, that's right. That's the answer to A. So now we've erased everything that depends on those 3 choices, and we've gone back to just what the swimmer does, whether we're watching or not. And for part B, what did it say was our choice of 0 position? The raft, yep. So this is our 0. What's the positive direction? Well, whatever we say is the positive direction is the positive direction. On a number line, you would think that would be the negative direction, but that's not like built into the universe. So we're saying that's positive now. That's positive. Okay. And so now we have to come up with the position labels. Well, so whenever someone's at the raft, they're at position 0. What's the distance between the raft and the shore? 50 meters. So if you start at 0 and go 50 meters in the positive direction, what's the position here? It's in the positive direction, so that would be positive 50. Okay. So this position label is positive 50 meters. And now the buoy. If you start at 0, this is the negative direction. Right. That's right. So if you start at 0 and go 25 meters in the negative direction, you're at a position of negative 25. And now we have to deal with the times. 0 time happens a minute before the swimmer leaves the shore. So a minute before this instant here. So at this instant here, what does the stopwatch read? Yeah, 1 minute. And it takes 2 minutes to get from here to here. So what's the label when the swimmer's at the raft? 3. Then 1 minute to get from the raft to the buoy. So what's the label at the next point? 4, yep. And then 2 minutes to get from there to the raft. So 6, yep. And now we're going to plot out these points. So the positions that matter on this graph are negative 25, 0, and 50. So I'll first just draw out the axes. So here's negative 25 meters. Here's 0. And here's positive 50. This is the position axis. And then the times that matter this time are 1 minute, 3 minutes, 4 minutes, and 6 minutes. And that's the time axis. Okay, so now what are the coordinates of that first point? When the swimmer leaves the shore, we're at 150. So the swimmer starts there. The next instant that matters is 3, 0. Okay, that's the coordinate. So here, next is 4, negative 25. And then last is 0. Oh, sorry, I did it backwards. 6, 0. Okay, so plot this, and it looks something like that. Okay, so you can see that, well, if I had done the scales exactly right, I just did it by hand, so this one looks sort of scrunched compared to that one. But if I had done the scales right, here's what you would see. Um, this graph is shifted up and down because of, what do you think causes a vertical shift in that graph? The choice of, so there's three choices. There's sort of three different kinds of, three things that happen. Um, that vertical shift is caused by your choice of the 0 position. Okay. Also, it's flipped upside down. What caused it to flip? Choice of the positive direction. And then it's shifted horizontally because of the 0 time choice. Yep. Okay. But the shape, and if you took like the absolute values of the slopes and the concavity and all that stuff, a lot of that stuff would be the same. Okay. So if so I guess the bottom line sort of is uh, both of those are valid position functions of time. There's nothing wrong with either of those. They're not exactly the same, and that's just built into how this all works. You have those three choices to make, and if you make different ones, your things look different. Okay. Um, Usually for us, um, instead of just plotting points like this, we'll usually have position as a mathematical function of time. Um, that's continuous and at least twice differentiable. And we'll see why it's going to be important to be twice differentiable uh, when we talk about velocity and acceleration. So, for example, um, we'll be given, instead of given these 1, 2, 3, 4 points and just drawing lines in between them, we'll be given something like position as a function of time is 2t cubed minus 20. Okay. And then from that, you know, if we wanted to know what the position was at time equals 0, we plug in 0 for t and the position would be 20. If this is an SI unit, so negative 20 meters. And if we wanted to know at 1 second, it would be negative 18 meters. Okay. Um, Displacement is very similar to position. Um, excuse me. But the way that displacement works is choose two times T1 and T2. Then the displacement from time 1 to time 2 is, so I'll write that as lowercase d. That's equal to the position at time 2, that later time, minus the position on 1. So T2 is the later instant. T1 is the earlier instant. Um, and can displacement be negative? Yes, if you're, you can imagine if you started with a more positive position than you ended, then you'll get a negative value for displacement. And that sign tells you something. So notice that the sign of the displacement tells you the net direction traveled from T1 to T2. Well, it it's two things. Okay. I'm talking about the sign of it, so I'm talking about direction. Um, but displacement has two bits of information built into it. The first one is its absolute value. So the absolute value is the distance between those two positions. That's not necessarily the total distance traveled, by the way, because um, the displacement doesn't know anything that happens in between those two spots. But the absolute value is the distance between the position at T1 and the position at T2. And second, the sign is, well, like I said up above, the net direction traveled from T1 to T2. Okay, so let me use the function example that I used a minute ago. So let's say that we know that position as a function of time is equal to 2t cubed minus 20. And let's say between time equals 0 and time equals 1 second, we want to answer these questions. Okay. First, what's the displacement? Yeah, right. And we're going to just come up with numeric values for all this stuff. Okay. So what's the displacement? The second one is what? Oh, yeah, 1 second. Sorry. What's the distance between the position at 0 and the position at 1? And what's the net direction traveled from 0 to 1 second? Okay, well, for part A, the displacement is going to be the position at the later instant, so position at 1 second minus the position at the earlier. We already calculated these two positions, so the position at 1 second was negative 18 meters. The position at 0 seconds, so minus the position at 0 seconds, which is negative 20 meters. And so the displacement is positive 2 meters. Okay, so even though both of those two positions are negative, even though this object stays on the negative side through this whole time interval, we have a positive value for the displacement. Um, what's the distance between those 2 points? Well, the distance between those 2 points is just the absolute value of the displacement, which is 2 meters again. And then the last one is, what's the net direction that the object traveled in that distance? It's in the positive direction. If we had come up with a negative displacement, it would have been in the negative direction. So the net motion is in the positive direction. Any questions about that? Okay, displacement is just a difference between two positions, so it has to have the same units as position. So units for displacement are length And that means that the SI units are meters. Okay. Now velocity, that's the next kinematic quantity that we have to define. And our definition for velocity is just a simple mathematical definition. Oh, we want to define instantaneous velocity, sorry. Just erase what you wrote before with your little electronic pen. There won't be any residue or anything because it's electronic. Instant. That's a electronic pen joke. Okay, instantaneous velocity. Um, so velocity as a function of time is just the time derivative of the position function. And you probably haven't seen this notation, or a lot of you probably haven't seen this notation before, but in physics and engineering, we use derivatives with respect to time so often that we have a shorthand notation for it. So derivative with respect to time is just shown as a dot on top of the variable. So this means the same thing as p dot. Okay. If you ever see a dot on top of a variable, that's what it means, derivative with respect to time. And so notice that means that on the position versus time graph, which is something we're going to see a lot, the instantaneous velocity is the slope at the chosen instant. And actually, let's make this number one. And I want to say one more thing that you need to keep in mind about the velocity. And that is the sign of the velocity an instant is the direction the object is moving at that instant. Um, okay, so let's do an example. Oh, let me give you the units. So units for velocity always have to be length over time. And so that means that the SI units of velocity are meters per second. Okay. And notice when I was talking about displacement, I said, where was it? Displacement has two pieces of information, okay? The absolute value is the distance, and the sign is the net direction. The same way that displacement has those two bits of information, velocity does too. This is the last thing I'm going to say. I mean, not for the semester. So velocity has two pieces of information. In it. First, the absolute value of the velocity. What do you think that is? Yep, good. So the absolute value of the velocity is the instantaneous speed. And the sign of the velocity is the direction of motion. Any questions? Okay, that's it. See you tomorrow.